Hello everyone, I've been told off, by the way, have you know, for not looking and sounding like a proper YouTuber. So here you go, who's going to do a proper introduction today. Yo, what's up guys? Here's another chemistry video from Phil, and I need you all to hit that like button, smash that subscribe button, and tell everyone about it. Actually, you know what? I think I'll just stick to being my boring self. Doesn't really work, does it? Anyway, here's a video continuing with topic 5.1. Today, my second video on this topic, and we're going to look at two types of graph in this video. Okay, now let's begin by saying if you are investigating a reaction, let's just say the reaction as shown there between A and B, there are two completely different methods that you can use to investigate the order of reaction with respect to, say, reactant A. Now, the first and obvious one, and we've already really looked at tables of data based on this, is what's called the initial rates method, and you would obtain data that looks like this. You do a whole series of different experiments, changing the concentration of A each time. We're keeping B constant, and from that we could deduce the order of reaction with respect to A, and obviously in this case it would be first order. Right, but let's be clear about that, what that would actually involve. You would have to set up a first experiment, possibly using apparatus like this, and you would measure the rate of reaction by just measuring the volume of gas produced in, say, the first 10 seconds, because you only want the initial rate, the rate at the start of the reaction. But you'd have to do it once using, say, A at 0.1. Once you've measured it for 10 seconds, you throw it all out, add fresh samples of chemicals, do the whole thing a second time, measure the volume of gas in the first 10 seconds, use that to get a rate, throw that out, do it again using 0.3, 0.4. That's 4 different experiments that you have had to do. And I know what some of you are already thinking. Those of you slightly lazily inclined, could mention some names, but probably better not. Oh, that's all way too much work, isn't it? I have to do 4 different experiments to get these results. Can't I just do a single experiment and work out the order of reaction from that? Well, the answer is yes, you could. You could do it using the continuous monitoring method. Now, in this, instead of, remember in the initial rates method, all you've done in each of these 4 separate experiments is measured the volume of gas after 10 seconds. That's it. You've taken one measurement from a gas syringe at one time interval and used that to get the initial rate. The alternative way is just, instead of carrying out 4 experiments, do 1 experiment only. But this time, instead of just taking one measurement after 10 seconds, you must measure the volume of gas after 10, 20, 30, 40, and so on. Often you would go on measuring actually for sort of 3 to 4 minutes actually. And although strictly, initially you would measure the volume of gas, by calculation you could work out the concentration of the reactant A at each time interval. And of course, A being a reactant, its concentration will drop. Now, so you could do it that way. This would be continuous monitoring. Let me just emphasize the essential differences. Initial rates method, several different experiments, but they're very short experiments, 10 seconds each only, and you take 1 measurement per experiment. Continuous monitoring, instead of having to do 4 different experiments, you've only got to do 1. The downside is, instead of just taking 1 measurement after 10 seconds, you've got to run the experiment for 3 to 4 minutes, taking a measurement every 10 seconds. Now, how would you deduce the order of reaction from the continuous monitoring results is the question. Well, the answer is plot the results on a graph. If the results end up, well, the graph ends up with this shape, then it is a first order reaction with respect to reactant A. If, on the other hand, the graph ends up being this shape, it is a zero order reaction, and you have to be able to recognize those two different shapes. So you will be adding these sketch graphs to your notes as instructed in the email. What about if A is second order? You might be thinking, well, actually your exam board does not require you to remember the shape of a graph for a second order reaction. Just out of interest, if you want to know what it would just be a much steeper curve following the shape of my finger there. It would still be a curve, but a much steeper curve to this side of it, whereas the zero order would have been a straight line to that side. But it's only first and zero that you have to remember. Now, however, wait a minute, what I'm saying here is sketch a graph and look at the shape. If it looks like a curve, it's first order. If it looks like a straight line, it's zero order. Now, hang on. If it looks like, we're scientists, we're not sociologists, are we? We don't settle, well, it looks like a curve or it looks like a straight line. We want precise method. After all, real experimental data might not quite be in a perfect straight line. What if your points look, you plot your points, you think, oh, they're a little bit all over the place. I've got a point here, a point there, a point there, then a point there. I'm not quite sure if it's a curve or a straight line. Yeah, sometimes it can be a little tricky. You're not going to get real experimental data in a dead straight line usually. So often you can pretty much tell whether it's first order or zero order from the shape of the graph, but pretty much tell is not good enough for chemists. We want to be certain. So there is a more precise way of being sure if a reaction is first. What you do is you draw some half-lives on your graph. The half-life is the time taken for a reactant's concentration to drop to half its previous value. Now, if reactant A started at 0.2, how long does it take it for it to drop to 0.1? We draw a line across at 0.1, we would do a dotted line downwards, and it would come to 7 minutes. So the first half-life was 7 minutes, the time taken to go from 0.2 to 0.1. We then do a second half-life. What if we want to half the conc again to 0.05? Well, we draw a line across at 0.05. If I do the line down there, it comes in at 14 minutes. Now, crucial thing here. Some careless students always just say, right, the first half-life is 7 minutes, the second is 14. Well, no, it is not. The first half-life is 7 minutes and the second is 7 as well, because the time taken for the concentration to drop from 0.1 to 0.05, well, it dropped by that much from 7 minutes to 14 minutes. So it took another 7 minutes. So both half-lives are 7 minutes. And if the half-lives are constant, then it definitely is a first order reaction. Now, of course, using real experimental data, sometimes the half-lives aren't precisely constant. You know, if the first half-life is 7 minutes and the second one is 7 minutes 10 seconds, that's still good enough to be first order, of course. If you're wondering, well, what is constant enough to be counted as constant? Well, as we say, strictly first order reactions will have constant half-lives. If the reaction is zero order, by the way, each subsequent half-life will half in value. In other words, if the first half-life is 10 minutes, the second half-life would only be 5 minutes. And, well, this handy little image shows them all together. If it's a second order reaction, then the half-lives will double. So strictly, when you're deciding are the half-lives constant enough to be first order? It will be first order if they are closer to being constant than they are to either halving or doubling. In other words, if the first half-life is 10 minutes and the second one is 11, that's fine, it's first order. But if the first one is 10 and the second one is 5, it's zero order. If the first one is 10 and the second one is 5.5, still zero order. If the first one is 10 and the second one is 20, strictly that's second order. But if the first one is 10 and the second is 19, that would also count as second order. Right, one other thing you can do from concentration time graphs, by the way, is to work out the rate of reaction at any given time. We actually did this in the first year in topic 3.5, so just a quick reminder. If you want to work out the rate of reaction at time t, t might be say 30 seconds, you put a dot at 30 seconds, draw a tangent and work out the rate by doing the change in the y-axis over the change in the x-axis. If you want to work out the initial rate of reaction, which sometimes you are asked to do, then you draw a tangent to the line right at the beginning of the curve. Often said to be a tangent at t equals 0. The line often starts off pretty much first. You could draw a tangent like that and work out the rate in the same way. That's the initial rate of reaction. One last very quick thing on conc-time graphs. You can also work out the value of k, the rate constant from the half-life. You do this strange thing, ln2. If you type that into your calculator, you've got an ln button, natural log. I won't dwell too much on what ln means now. We will do in a future lesson, by the way, but not for now. You just do ln2, which actually just comes to 0.693 anyway, divided by the half-life, gives you the value of k. Right, so that's concentration time graphs dealt with. Remember, they are drawn from results obtained from the continuous monitoring method. There is this second method, initial rates method. If you use that method, you can also plot graphs of your results. Often you can simply tell the order of reaction from the data, and it's not necessary to actually plot a graph. But if you were to plot a graph on this, you would plot the graph of concentration of A, which would be the independent variable, against the initial rate. And again, you can use the shape of that graph to deduce the order of the reaction. So it's fairly straightforward stuff. If it's a straight line, then the rate hasn't changed as the conc has increased, and therefore it is naturally zero. First order would, of course, look like that. As the conc increases, the rate increases proportionally. And one other thing about that graph, as it says below there, if you measure the gradient of that graph, again, by doing the y over the x value, you don't actually have to draw a tangent this time because it's a straight line anyway. But if you measure the gradient just by, say, drawing a triangle there and doing the y over the x value, that would give you the value of k, but only if the reaction is overall first order. Not just first order with respect to reactant A, it would have to be an overall first order reaction. In other words, if there's a reactant B, then B would have to be zero order. If B is zero order and A is first order, then the gradient of that graph would equal the value of k. As for second order reactions, and if you want to pause the video for a minute and just have a think for yourselves, what would the shape look like there? Okay, answer is that. Well done. If you came up with that, the concentration and the rate are not proportional anymore, because of course if you double the conc, the rate would go up by 4 times. You get an exponential type line this time. Okay, that's just about it for today, really. As I've mentioned in the email, it's now a matter of just taking notes of the appropriate slides. You do have to be able to recognize and recall the shape of a conc-time graph for a zero and a first order reaction, and a rate-conc graph for 0, first and second. So you will sketch the slides as instructed, but to fully understand this, you of course need to do some questions and draw some graphs for yourselves. So you also need to do sections C, D and E on the question sheet. Okay, I'll leave you to get on with that. That's all for now. Bye.